Hello and welcome to today's class. Today we'll have a look at a couple of things which we can use to work out the pressures and therefore the velocities of fluid flowing both internally within a pipe and also externally around an object. We saw in the Bernoulli's equation video how pressures and velocity are linked by considering the energy associated with the fluid flowing through a pipe. We talked about this idea of pressure associated with, or energy associated with a pressure, or the kinetic energy, or the potential energy, and how this can't be created or destroyed from one point to the next. So if you've not seen that video already, have a look at that video. Okay. Once we understand the idea of what Bernoulli's equation is all about, we can apply that to manometers and pitot tubes, and that's what we're going to be doing today. So we'll have a look at manometers, we'll have a look at single limb manometers, we'll have a look at U-tube manometers, and constant origin manometers, inclined manometers, and then finally barometers, which is the same really. You're using a column of fluid to represent a pressure. Nowadays, you don't tend to see that. Actually, you don't tend to see a pressure being represented by a column of fluid. You will see potentially just a digital readout, a digital equivalent. You might have something, a diaphragm or something like that, linked to a pressure, linked to a digital readout, and you'll just simply read that. Manometers will use mechanics. You use this idea that a column of fluid represents a pressure. We know pressure is rho GH, the hydrostatic head associated with the column of fluid. So we'll have a look at manometers. We'll then move on and we'll have a look at pitot tubes. Pitot tubes are often linked to manometers. Pitot tubes are used to measure the velocity of a fluid flowing past an object. We know from Bernoulli's equation that fluid velocity is linked to pressure. So therefore, if we point our pitot tube into a velocity, into a fluid which is moving, and link that to a manometer, we can measure the pressure differences associated with the fluid flow, and therefore we can work out the velocity differences, the velocity of the fluid flow. So we'll have a look at pitot tubes as well in today's class. Okay, so that's the plan. We'll have a look at manometers and then we'll move on and we'll have a look at pitot tubes. So manometers are used to measure the fluid flow through a pipe. We saw in the last video, when the video looking at Bernoulli's equation, that pressure and velocity and also potential energy are linked from one point to the next, and we can assume that that is constant if there is very little or zero energy loss due to friction and turbulent flow and so on. So we can consider this situation here. Here is a pipe. We've got a constricting pipe, fluid flowing from left to right, from position A to position B. We know through conservation of mass that the fluid must be travelling faster in position B than it is at position A. If the fluid is flowing faster at position B, the total energy is the same, the pressure must be reduced. So our height at position 2 or position B here, sorry, would be lower than the height of the fluid at position A. So we saw this idea last time, this idea of fluid flowing through a pipe, and we've got pressure taps coming in there, showing columns of fluid which represent the pressure from one position to the next. And that's essentially what a single limb manometer is. Essentially, it's a pressure tap, and it uses this idea of hydrostatic head of fluid to represent the pressure at a particular point. So the gauge pressure at position A, rho GH, our density times by our gravity times by our height. Notice that is the gauge pressure. There's also the atmospheric pressure sat on top of our manometer here. Okay, so it's not absolute pressure, it's gauge pressure. So our gauge pressure at point A, rho G H1. Our gauge pressure at point B, rho G H2. PB less than PA due to the fact this pipe is constricting. So therefore the conservation of mass tells us that the velocity must be increasing. Therefore the kinetic energy is going to be increasing if the total energy between A and B is the same. If the kinetic energy is greater here, and it's the same potential energy, it's the same. This is a horizontal pipe here. The kinetic energy is increasing, therefore the energy associated with the pressure must be decreasing. So therefore PB is less than PA. So a single limb manometer. A U-tube manometer uses the same concept. However, as the name suggests, our manometer now, rather than being a straight pressure tap, we've got a U-tube. Now, what does that enable us to do? Well, as the fluid moves around that tube, the position of that fluid will tell us the pressures which are the tube that the fluid is exposed to on this side of the U-tube and on this side of the U-tube. So here we've got our U-tube manometer attached to this object here, which has a pressure P, and that is exposed to this fluid here, and that is forcing our fluid around our pipe here. And here you can see it's exposed to atmosphere. I've got our atmospheric pressure. Because our fluid has moved around this direction here, we can clearly see that the pressure inside our vessel here is greater than atmospheric pressure. Now, how much greater is dependent on this height here, H, rho GH. So what we would do, we just draw a datum point through there, and we know the pressure on that dotted line there. Pressure here is going to be the same as the pressure here. And the pressure here would be P, pressure here would be our atmospheric pressure plus this column of fluid. The hydrostatic pressure caused by that column of fluid. Okay, so P minus P atmospheric pressure, therefore, would be rho GH, the height of the fluid. So our basic U-tube manometer, that's what we do. We would draw a line typically where our two fluids interact, and we draw a line through there, and then we say the pressure at this point here is the same as the pressure at this point here, and we just look to see what is causing that pressure. In this case it's P, and in this case over here it's our atmospheric pressure plus this hydrostatic head. So that's our U-tube manometer. So in our U-tube manometer, the pressure difference P1 and P2 causes the fluid to move around the U-tube manometer. In our constant origin manometer, the pressure difference P1 and P2, instead of the fluid moving around the tube, we simply get this height here, Z2, changing. Now the reason for that is that A1 is much greater than A2. So as the name suggests, it's a constant origin. This origin here, XX, doesn't change very much because we've got such a large area here. Okay, so even if P1 were to change, that's going to result in a really small change in this fluid height here. So actually we can negate that. We can say basically that's constant. So if A1 is significantly larger than A2, you've got a constant origin manometer. Now, if you've got a constant origin manometer, it's just this height here, Z. So the height of the fluid above that constant origin, which tells us the pressure difference between P1 and P2. So P1 minus P2 equals rho GZ. We've got a constant origin manometer. Our inclined manometer is used where we've got very small changes in P1 and P2. So the change in the height actually wouldn't be very much. So that would be really quite difficult to measure. This height here, H, would be difficult to measure. So simply by inclining the manometer. Here we've got our manometer inclined at some angle theta. Means that instead of measuring our vertical distance, we can measure the distance along the manometer. Okay, so the change in length here is obviously related to the change in height. We can just use a little bit of trig, and instead of having a very small distance here, we can have a much larger distance here, which we can measure more easily depending on the angle of theta. P1 minus P2 equals rho g h equals rho g L sine theta. That should be, not alpha. So rho g L sine alpha is dependent on the angle that the manometer is inclined at. Generally, that's quite small, alpha between, or theta between 10 and 30 degrees. And finally, barometers. Barometers are using columns of fluid to measure the change in atmospheric pressure in much the same way. So here we've got a barometer, we've got a vacuum in our tube here, so P equals 0 in the tube here typically, and our mercury is exposed to atmospheric pressure. So as the atmospheric pressure increases, that column of fluid will clearly increase. As our atmospheric pressure decreases, that column of fluid will decrease. The pressure difference is less, so therefore the height of the fluid will be less. So our atmospheric pressure is given by rho g h. And on that tube then you would write sunny weather, or cloudy weather, or rain, or storms, or whatever, because clearly the height of that tube, the height of the column of fluid in that tube is related to the atmospheric pressure, which in turn would be related to our weather conditions. So we've seen today that a pressure difference can be represented by a column of fluid. That column of fluid represented by rho gh, the hydrostatic head, which is causing that column of fluid change, that height change. We also saw in the Bernoulli's video that velocity and pressure are related, are linked. We know that kinetic energy and potential energy and pressure from one point to the next remain the same if there are zero pressure losses. So that's the concept, that's the idea of pitot tubes. Pitot tubes would use that concept to try and understand the velocity of a fluid flowing around an object. And what a pitot tube will do, it will measure the dynamic pressure against the static pressure, and use that pressure difference to work out how quickly that fluid is moving. So here we've got fluid flowing past an airfoil and flowing from left to right. Our velocity is u1, p1 upstream. At the front here, we've got something called the stagnation point, where our velocity is 0. And obviously, if our velocity is 0 there, our pressure must be a maximum. So at the front of the object, and then our velocity increases and flows around our airfoil. So if Z1 is equal to Z2, i.e. this is horizontal, we know from Bernoulli P2 plus half rho U2 squared equals P1 plus a half rho U1 squared. Now, if U2 is 0, which is what we see at the stagnation point there, so U2 is 0, so this term disappears. P2, our stagnation pressure, equals P1 plus a half rho U1 squared. So if we measure the pressure at various points of fluid flowing past an object, and we link that to a manometer, and that's related to a height of fluid, so our hydrostatic pressure, we can calculate the velocity of the air flowing around that object. And that's something that you would see. Here's an example, an aircraft, and quite often you'll see something like this sticking out the front of the aircraft. And what that is a pitot tube. So that's been placed there to measure the velocity of the fluid flowing past the object. Now, if the object is moving through the air, as this aeroplane is, that will give you the air speed. Okay, now that's not necessarily the same as the ground speed because it's dependent on whether or not the air is moving relative to the ground, but that will give you the air speed of the object moving through the through the air, through the fluid. Okay, so a pitot tube, a small diameter right-angled tube used to measure the pressure, used to measure the total pressure. So what's actually going on inside this object here? Here we've got a schematic of what's going on. Okay, so we've got our fluid flowing from left to right, and as our fluid flows from left to right, we've got a right-angled tube, our pitot tube sat inside that. So if our fluid is flowing in this direction, clearly if it's got a horizontal component there, it has 0 vertical component, so it's not flowing into my tube at all here. Simply that is being exposed to atmospheric pressure. So our total pressure equals our static pressure plus rho half rho u squared. Okay, so therefore we can work out the velocity of the fluid based on that pressure difference. So what does the pitot tube actually do? Well, it measures the dynamic pressure, which is, so here we've got the same scenario. We've got our fluid flowing from left to right. We've only got a horizontal component. There's 0 vertical component. So at position X here, which is exposed to this part here, that is exposed to atmospheric pressure. It's outside. It's also exposed to dynamic pressure due to the fact that this fluid is moving at a certain velocity. So X is measuring static pressure and dynamic pressure. Okay, so that gives us our total pressure. However, because our fluid has 0 vertical component, Y here, this inlet here, is only measuring static pressure. There's 0 dynamic pressure. The fluid flowing in this direction does not contribute anything in terms of the dynamic pressure because there's 0 vertical component. Okay, so the tube on the outside here, we've got 2 concentric rings. So if you were to look from left to right and from this position here, look in this position here, what you would see is there's 2 concentric rings. X here, P1, Px, that is the total pressure, static pressure plus the dynamic pressure being exposed to the tube, to the pitot tube at position X. This point here, this tube on the outside, is only being exposed to static pressure. There's 0 dynamic pressure. So Py would be our static pressure. So we've got 2 different pressures. If we were then to link that to a manometer, we would expect to see our column of fluid move. Okay, so our static pressure, Py, and our total pressure, Px, in the center of the tube. Okay, and the difference between those two, the total pressure minus the static pressure, is going to be rho g half rho u1 squared. So the column of fluid is going to be related to the dynamic pressure. The dynamic pressure is going to be related to the velocity of the fluid. So therefore we can work out how fast our object is moving through that fluid. So that's what a pitot tube does. There we've got an example, a modern example of the sort of thing that could be set up if you've got a pitot tube or an array of pitot tubes. You could arrange them like this. For example, here we've got a Formula 1 car. Here they're clearly using a digital equivalent. They've set up a matrix of pressure sensors behind the wheel. They'll then drive their vehicle so that you can get a profile of the pressure around this area here. Okay, so we get some understanding of how the wing and the wheel and so on lead to pressure changes. Clearly, that's important in this instance. You could set up exactly the same thing if you had a matrix of pitot tubes so that you could measure pressure at various points and therefore you can, by considering the airstream velocity, you can work out the pressure differences at various points for that vehicle. So we've gone through two different examples there, so two different handouts looking at manometers and then moving on and looking at pitot tubes. I'll upload those two handouts. This first one looking at manometers, so single limb manometers, U-tube manometers, constant origin manometers, inclined manometers, and then barometers. And at the end of that handout, there are some examples. There are, what have we got? 6, 7, 8, 9 examples at the end there. Have a go at those examples. And we will discuss those in class. I will also upload solutions to those examples. So this handout here, I'll upload that as well. Those examples, you can see they go through all of the manometers that we've discussed there. The only slight complication, the only slight addition there is this idea of having an inclined U-tube manometer. If you've got two fluids, here fluid 1 going through our pipe and fluid 2, we're using a U-tube manometer to measure the size of this obstruction inside our pipe. So you might have some, I don't know, some corrosion or something like that, and you want to measure that, you want to try and quantify that, so you can look at the upstream pressure and the downstream pressure, and by comparing those, that will give you an indication of the amount of corrosion between the upstream and the downstream points. Okay, in this instance, fluid 1 is clearly denser than fluid 2. So you might use an inclined manometer, or sorry, you might use an inverted U-tube manometer when the fluid in the manometer is of a lower density than the fluid that you're trying to measure. So here we've got fluid flowing through our pipe, and here we've got a lower density fluid in our manometer. So therefore we've had to invert the manometer so that we can understand what's going on. Okay, but the process is exactly the same. Okay, so we draw our datum point here, XX, and we'd work our way around to get to this point here. We'd work out the pressure at this point here. That's the same as the pressure at this point here. The pressure difference is caused by this height of fluid, and therefore we can work out what that pressure difference is caused by that height of fluid. So have a go through those examples. There's some basic U-tube manometer examples, inclined manometer examples, inverted U-tube manometer examples, and so on. So have a look at those. So that's the first handout that we've been through today. The second handout that we've been through today is this pitot tube handout. I'll also upload this. So this talks a little bit about the theory that we've already discussed. And then at the end of that, again, there's some examples. There's 1, 2, 3, 4 examples there using pitot tubes. And there you can see an example of a pitot tube connected to a manometer so that we can work out the velocity of the fluid coming out of that box. Okay, so and again, I will upload work solutions to those examples, so you can see there's those solutions there. So I'll upload those handouts with the theory and the questions on them. I'll also upload the work solutions to those questions so that you can try those. Okay, have a look at those examples. Think about the theory and reflect on the theory that I've been talking about today, and then in class, then we will, if you've got any questions regarding the theory or any of the questions, any of the examples at the end of the handouts, we can go through those together. Okay, so have a look at that, and I will see you next time. Okay, thank you. Cheers. Bye bye.